Welcome to the FABRICATE virtual reality simulation created by the University of Texas at Arlington's Human Factors Lab. The FABRICATE software is a fully accessible bilingual reality interface for constructive AM training and education. This software was created with the assistance of funding from the National Science Foundation. Let's get into it. Upon loading into the menu, the user can select a variety of options, including English or Spanish for instructions. The user's name and the class they are taking that uses the simulation can be inputted to save their progress for data collection. They can also choose to use either the powder bed fusion or hybrid machine module and can choose between several different learning stages. These stages include a tutorial mode that teaches the user how to use the VR controls, learning mode to learn about the machinery and materials, training mode to learn the process of manufacturing with the machine, and testing mode to test their learning. We will be starting with the tutorial mode. In tutorial mode, the user learns how to use the virtual reality headset controllers and how to perform common tasks in the simulation, such as interacting with UI screens, teleporting, grabbing objects, and moving objects. Now we will demo the learning module. In learning mode, the user will get a feel for the equipment and materials used to manufacture a part using a powder bed fusion printer. The user is taught which pieces of personal protective equipment they need to use and why they are important. They then equip each piece of safety equipment and answer comprehension questions to ensure that they were paying attention to the safety equipment information. Next, the user learns about their available material options and the strengths and weaknesses of each material, including each material's cost. The user also learns about the build platform, which is a container that the part is printed inside of. The user then learns how to place the build platform inside of the 3D printer. Now, the user learns how to load the powder box into the printer. At this stage, the user learns about different parts of the 3D printer and the significance of each part. The user now learns a process to remove the build platform from the printer. They learn to first unplug the electric cable connecting the build platform to the printer, unlock the lock, and finally remove the build platform. Completing these steps in the right order is important to ensure the operator and equipment are unharmed. Now, the user learns about what to do with their printed product after it is finished printing. They must take the build platform containing the print to the post-processing station, where they clean up the printed product and prepare the build platform to be used again. The user also learns about the parts of the post-processing station and how to use each one. The learning module is now complete. The user can see the correct answers to the comprehension questions, so they can see what they got wrong, as well as their total accuracy. We will now demo the training module of the Powder Bed Fusion 3D printer simulation. In this module, the user learns the full process of printing and cleaning a part made using this printer. While the last module focused more on providing information about the materials and equipment, this module focuses on how to use the equipment. The user starts by equipping their personal protective equipment, just as they did in the learning module. Next, they load the build platform into printer. Now, the user learns how to select the right parameters to 3D print a part. We chose to print out landing gear for a drone in the Start menu, so the instructions will be tailored to what parameters work best for landing gear. The user is instructed that high structural strength, smooth surface finish, and impact resistance are important for drone landing gear, which will inform their later selections of which parameters to choose for the 3D print. The user now learns how material layer thickness and build orientation impact their final product. They are given quizzes over this information to ensure their comprehension. Once they have learned about each process parameter, they make their selection of what they think will work best for the drone landing gear. If the user chooses an option that will not work well for the part that they are printing, they are instructed that the option they chose is not optimal and to choose a different option. This feedback ensures that they are choosing wisely and truly learning how to choose the right process parameters. The user now inserts a material that they chose during process parameter selection into the printer. Now that all process parameters are selected and the build platform and powder box are loaded into the printer, the user can start printing. After the part is printed, they must wait for the build platform to cool down, just as they would with a physical printer. The user now removes the build platform from the printer and loads it into the post-processing station. The user cleans the printed product with a brush to remove any excess powder. The excess powder is collected by the vacuum in the post-processing station and can be reused in future prints. The training module is now complete. The user's accuracy in answering comprehension questions and the right answers to the questions are provided, just as they were in the learning module. We will demo the testing module now. This module provides limited instructions and assistance to the user and is designed for the user to be able to test their learning from prior modules. The user still answers comprehension questions as they navigate through the simulation. They complete all the same steps as they did in the training module, just without any hints from the simulation. The information on the process parameters is not provided in this version. They must make an informed decision about which parameters to choose based on their understanding and memory from prior modules. At this point, the build platform has been loaded into the printer, but not the powder box. If the user tries to start printing without both of these parts loaded, they will get an error. The user must remember which material they chose in process parameter selection and load it into the printer. We chose nylon 11 CF, so we will load powder from this powder box. We will make sure the lid of the powder hopper is closed before we start printing. Now that both the build platform and powder are loaded into the printer, we will start printing. Now, the user removes the build platform and loads it into the post-processing station, just as they did in the training module. We will now clean the freshly printed part with a brush. The testing module is now complete. We can see our accuracy in completing the training steps and comprehension questions, but we are not provided the correct answers in this version. We will demo the hybrid machine simulation now. The same kind of information that was provided in the learning and training modules of the last machine are provided in a single module for this machine. The process of making a part with a hybrid machine is more complicated, and creating many different modules for this machine would add too much complexity to the simulation. The user starts by reading the problem statement, which instructs the user that they are to fix or replace a damaged jet engine turbine blade as quickly as possible while keeping quality high and production costs low. Just as in the powder bed fusion simulation, the user answers questions as they progress through process parameter selection to ensure their comprehension. The possible methods that the user can fix the turbine blade with using the hybrid machine are provided. They can choose to manufacture a new blade using a CNC-only process or additive plus CNC process. Alternatively, they can repair the existing blade using a flat, finger, or scallop joint interface. The user is also tested on how the repair process works. If they are unsure, they can press the previous button to reread the previous screen. The pros and cons of each method of repairing or replacing the turbine blade are provided. The user must use this information to make an informed decision about which process to choose. The user is tested on what effect the pros and cons of each method will have on different objectives, such as minimizing environmental impact. The pros and cons of fabricating a new turbine blade using an additive plus CNC process are now provided. Now that the user has seen both methods of manufacturing a new turbine blade, they are asked to compare the two and give reasons why they would choose one method over the other. The information for first repair option, a flat joint interface, is now provided. The user must now compare repairing the blade with a flat joint interface to replacing the blade. The user is now presented with pros and cons of a second method of repairing the turbine blade, a scallop joint interface. What are the differences between this interface and the flat joint interface? The final method of repairing the blade, a finger interface, is now presented. The user is now presented with the objectives given to them by the problem statement and ranks based on importance them using two different methods, rank averages and pairwise comparisons. With the rank averages technique, the user ranks the objectives from highest priority to lowest priority, and their ranking is averaged with the ranking of the other evaluators to provide a final rank. The pairwise comparisons technique is now presented. The user compares each objective against each other and chooses which of the two objectives is more important. The objective with the most selections has the highest rank. Before the user makes their selection of which process to use, they are given a summary table of the traits of each method. The user now chooses whether to repair or replace the damaged turbine blade, and which method of repairing or replacing the blade they will use. We will show all of the methods, starting with repairing the blade using a flat interface. The user must first put on all of their safety equipment. Now, the user will teleport to the hybrid machine's control panel to turn on the machine. The doors of the hybrid machine are opened and closed to calibrate the door close sensor. Since we are repairing the broken turbine blade, we will load the broken blade into the machine's fabrication area and secure it into place. Instructions of what to do and where to go are provided to the user in a floating UI window that follows their vision. This module requires lots of moving around the virtual environment, so keeping the instructions in the user's field of vision is important to ensure that the user doesn't miss any instructions. Once the turbine blade is secured into place with a wrench, the wrench is put back into its place and the machine doors are closed. Now, the user will learn how to load powder into the machine. This powder will be solidified with a laser by the machine to form the fabricated part. To start, The powder and funnel are removed from the cabinet, and the glass protective shield is removed from the side of the machine. Next, the screws of the powder hopper are unfastened, and the top of the hopper is removed from the machine to reveal the opening to load powder into. The powder vacuum is now turned on and moved into position, which will minimize dust particles during powder loading. The top of the powder container is removed, and the funnel is placed on top of the powder hopper to prevent spillage. The powder can now be poured into the machine. After the machine is filled with powder, the powder container and funnel can be removed, the lid of the container is rescrewed, and the vacuum can be turned off. The user puts back the powder hopper lid and refastens the screws. Once the glass shield is refitted to the side of the machine, the powder container and funnel can be put back in their cabinet, and powder loading is complete. Now, the user will select the tool head to be used by the machine. We will be repairing the turbine blade using a flat interface, which begins by using CNC to file down the broken edge of the turbine blade. Since the process begins using CNC, we will start the machine with the T10 head. The user now locks the doors to the fabrication area to prevent them from opening during fabrication. The fabrication process involves metal shards, lots of heat, and gases that the operator should not be exposed to. The key is then placed into the laser controls to enable the laser for the additive portion of the fabrication process. The additive control screen is checked to ensure that all necessary systems for additive printing are operational. The user now selects the G-code program to run on the machine. This program tells the machine which direction to move the head in, which head to use, and other parameters necessary to fabricate the desired part. We will load the G-code for the flat finger interface. Once the user presses cycle start, you can watch the fabrication process through the doors. The turbine repair is now complete. Next, we will demo the steps taken to repair the turbine blade with a finger interface. Since the finger interface is a CNC plus additive plus CNC repair process, just like the flat interface, the only real difference in the machine preparation is that a different G-code program is loaded. All other steps, including powder loading, locking the doors, and laser activation, are identical to the prior method. However, we have included a full playthrough of the finger interface for thoroughness. The user first equips all safety equipment. Next, the user turns on the machine. You can see the green light on the top right of the control panel turn on after the power up button is pressed. The doors are cycled and the broken propeller blade is loaded into the machine's fabrication area, just as before. The user now loads powder into the machine. Next, we will switch out the tool head currently on the moving arm of the hybrid machine for the CNC tool head, which is the T10 head. The doors to the fabrication area are locked, and the key is used to turn on the laser controls. Don't forget to check the status of the additive machine parts on the additive control panel. Now we will select the G code for the finger interface to run and start the fabrication cycle. Notice that the file name of the G code selected is different from the G code used by the flat interface process. Fabrication has now begun. Notice that instead of the CNC head filing the turbine blade down to a flat surface, it leaves a finger-shaped ripple on the surface. We will demonstrate the scallop interface repair process now. Preparing the hybrid machine to repair the turbine blade using the scallop interface repair process is identical to the last two CNC plus additive plus CNC processes, except the user will select the scallop interface G code. The user puts on their safety equipment, just as before. The user now turns on the machine. The doors are cycled and the broken propeller blade is loaded into the machine. The user now loads powder into the machine. The head on the fabrication arm of the machine is switched out to use the T10 head. The doors are now locked and the laser controls are turned on. The user loads a scallop G-code and then begins fabrication. We will now demonstrate the processes used to replace the turbine blade, starting with the additive plus CNC process. Safety first. We still need all of our safety equipment. We'll turn on the hybrid machine using the same process as before. We'll cycle machine doors, but instead of loading the broken turbine blade into the machine, we'll load a build plate that will be used as the foundation for the machine to build a new turbine blade on top of. The build plate is loaded into the machine in the same fashion as the broken turbine blade. This method of replacing the turbine blade requires additive fabrication, so we'll need to load powder into machine. We'll now select which tool head to start the fabrication process with. Since this process starts out using additive fabrication, we'll select the T08 head instead of the T10 head. We'll now lock the machine doors and turn on the laser, just as before. Now, the user selects the Additive plus CNC Replacement Turbine G code and starts fabrication. The final method of replacing the turbine blade included in the FABRICATE simulation is the CNC-only method. This process does not use additive manufacturing at all, so it does not require powder to be loaded into machine or for the laser to be enabled, making it the simplest method in the simulation. The user turns on the hybrid machine. The doors of the machine are cycled, and a block of metal is loaded into the machine that will be filed away to create the shape of the turbine blade. The powder loading step is skipped, and the user can go straight to selecting the CNC tool head. Now, the user can simply load the CNC Methods G-code and start fabrication. Thank you very much for watching this demonstration of the University of Texas at Arlington Human Factors Lab's Fabricate simulation. If you have any questions, please leave a comment or get in touch with any of the individuals listed on the screen. We appreciate your interest in our work.